Where we had left off at the end of the last class meeting was, I believe, defining beta, our common emitter current gain, which relates to our collector current IC. And then we applied Kirchhoff's current law over the terminals of our device to find that the emitter current is simply the base current IB plus the electric current, or excuse me, plus the collector current IC, and come up with this relationship. Beta plus 1 over beta times IS EXP to the base emitter voltage divided by VT is our emitter current. So what I want to discuss now is alpha, okay? So in some instances, an alternative transistor parameter alpha can be used to simplify things, okay? Alpha is what's called the common base current gain. And it is defined as the collector current divided by the emitter current. And it relates to beta by the relationship beta over beta plus 1, which means that alpha will always be a quantity less than 1. Okay. So we can summarize all of these relationships as follows. IC is equal to IS, our saturation current, EXP VBE over VT. Our base current IB is 1 over beta times IC, or 1 over beta IS EXP VBE over VT. In terms of alpha, this is going to look like 1 minus alpha divided by alpha IS EXP VBE over VT. And then we have an emitter current, IE, is equal to 1 over alpha IS EXP VBE over VT, or beta plus 1 over beta IS EXP VBE over VT. These are all the different ways to express any of the 3 currents in an NPN bipolar junction transistor, depending on whether or not we know alpha or beta. So let's say that in a particular circuit, we have an NPN BJT whose base current is IB is equal to 20 microamps, and whose emitter current is equal to 1.5 milliamps, when we have a base emitter voltage VBE is equal to 0.8 volts. And we want to determine alpha, beta, and IS, or saturation current density. I'm having us work this problem. It's actually a little bit ahead of time. In 339 next quarter, you guys are going to be dealing with practical BJT circuits, where the values of these quantities, alpha, beta, and IS, are expected to vary some from the data sheet. And it will be necessary for you to know what the actual value of the device you're working with is. And you determine that by measuring quantities, right? So with these three measured quantities, how can we figure out what these data sheet parameters are? Anybody have any thoughts? Anyone? Okay, so the collector current, if we know the base current, we need to know beta. And if we want to find the collector current, but we know the emitter current, then we need to know alpha. And those are two of the quantities that we don't have. So how do you suggest we determine the collector current? Okay, so the collector current. Okay, I see what you're seeing here. All right, so IC is IE minus IB. Okay, let me get my calculator out because that was not the way I was expecting you guys to approach it, but that's perfectly okay. So that's going to be 1.5 milliamps minus 20 microamps gives me 1.48 milliamps. All right, so Preston, what can we do with that? Okay. Alpha is IC over IE. That's 1.48 milliamps divided by 1.5 milliamps, or 0.987 repeating. All righty. What's next? So if we know IC, it should be trivial to determine beta as well, right? Because beta is simply IC over IB. So that would be 1.48 milliamps divided by 20 microamps, which is 74. And then how do we determine IS? Yeah, so we can use this top equation and simply divide IC by the exponential of VB over VT. I'm mildly amused as I work this problem two different ways, neither of which was as obvious as what Preston suggested. So good on you, sir. IC over EXP, VBE over VT. And we will get 6.417 times 10 to the negative 17 amperes. All right. So what I would like to do now is introduce some circuit models for our transistor, okay? These are going to be large signal models, all right? So the first thing that I want to do is introduce our schematic representation, all right? So this is the schematic symbol for an NPN bipolar junction transistor, where the C terminal obviously means collector, the B obviously means base, and the E obviously means emitter. And it's drawn in such a way to where the collector, which is at the highest potential for a forward active circuit, is on top. And there is an arrow indicating that current should be flowing out of the emitter terminal, okay, for an NPN BJT. Now, this schematic representation doesn't do anything to help us actually analyze BJT circuits. This is just a simple representing a BJT, okay? So we are going to have two very related large signal models that we will use in place of this. So similar to how we had a practical op-amp model, having a dependent voltage source and a couple of resistors and all that jazz, that we could substitute in to do analysis whenever we couldn't use the ideal op-amp rules. We're going to have something similar to that here, okay? So let's talk about what we think should be in our BJT model. So what do we see in the reverse, or excuse me, the forward active region? What do we see between the base and the emitter? It's not a trick question. There will be a voltage drop, okay. Let's start there. So if this is the base terminal, down here is the emitter terminal. We will have some voltage drop. VBE, I can agree with that. But what does that voltage drop literally occur over? PN junction or diode, right? A forward biased diode. So we're going to have some base current, IB, flowing in, which flows through our forward bias diode, generating some base emitter voltage VBE, or we can think about it the other way around. We have some voltage drop VBE, which causes some base current IB to flow. Either way works. All right. Over here on the right-hand side, let's put our collector. Okay. So between the collector and the emitter, we have a reverse biased PN junction, which arguably, based on just our knowledge of PN junctions, means that it should just be open circuited. But we have a caveat here, right? Because we've designed our device in such a way that the width of that base is very small, which means that electrons that are emitted by the emitter get swept through to the collector, right? Which means there's definitely current flowing between the collector and the emitter. There has to be in our device, okay? The current that's flowing between the collector and the emitter is dependent on that voltage VBE, which is what our mathematical model describes, right? All of our currents are dependent on the exponential of VBE minus or over VT. So between these two terminals, we are going to put a dependent current source having a value of IX, EXP, VBE over VT, where this represents our current IC, and this represents our current IE, so that we can easily see our collector current depends on our base emitter voltage, the forward bias drop over that diode between the base and the emitter terminals. And we can also see that IC and IB add together to form IE. So this is what's known as a voltage controlled current source model, because the current flowing from the collector to the emitter is controlled by voltage. Fairly straightforward, right? We can change this model very, very slightly by looking at the exact same situation from a slightly different perspective. If we say that this current IB induces isn't the right word here, but this current IB causes this voltage VBE to occur, which in turn causes this current IC to flow down, we could develop a current controlled current source model. There we go. That looks something like this. Where this is our base. This is our emitter. This is our collector. We'll do our terminal currents real quick. This is still the voltage drop, VBE, but now we simply represent our current, our collector current by beta IB. So we have a voltage controlled current source model and a current controlled current source model, and they can be used absolutely interchangeably. But I would argue that anytime we know what the base current is, we use the current controlled current source model, and anytime we know what the base emitter voltage is, we use the voltage controlled voltage source model. And if we don't know either, we just use whichever one seems like it's going to be easier. That's literally the distinction there. Okay. So with that in mind, let's say that we have the following circuit. We have a 2-volt supply voltage being applied at one leg of a 500 ohm resistor, which I'm going to label RC. This is attached to the collector terminal, excuse me, of our device. And then out here at our base, we have a voltage of 0.8 volts applied. If IS is equal to 5 times 10 to the negative 17 amps, and beta is equal to 100, I would like for us to determine the following quantities. Our collector current IC, our base current IB, our emitter current IE, and finally the output voltage of this guy, V out here, which is nothing more than the collector emitter voltage, VCE. All right. So for this trivial of a circuit, it's really not necessary for us to use our large signal model, but I'm going to do it just to get you guys into the practice of doing it. Okay. So for this particular circuit, it would look something like this. This is our voltage VBE ground, so we have 0.8 volts. Here we have 2 volts. Our 500 ohm resistor. This is my base current IB. This is my collector current IC. This is my emitter current IE. So, which representation of the large signal model do you think we should use here? The voltage controlled model, right? Because we know what VBE is. We can read it off of there and see that it's 0.8 volts pretty trivially. Okay. So IS EXP VBE over VT. Collector, and I can say that my output voltage, I'll try to tuck it down in here, as the voltage drop between my collector pin and ground. So it's a voltage drop over the combination of this 500 ohm resistor with this 2 volt source. Does that seem like a reasonable way to express that? Okay. So how can I determine any of these quantities? Yeah, IC is trivial. We know what VBE is, right? So IC, so run out of space here, is IS EXP VBE over VT. If we plug in our numbers of 5 times 10 to the negative 17 for IS, 0.8 for VBE, and we're making the assumption that VT is 26 millivolts. This comes out to be 1.153 milliamps. And I'll go ahead and write that up here. VT is 26 millivolts. Once we know IC, IB is simply IC over beta, 11.531 microamps. IE is simply the sum of IC and IB, which comes out to be 1.165 milliamps. So all of our terminal currents for our transistor are fairly trivial. Once we know IC, we can get the other two by just using beta and then applying Kirchhoff's current law. So now comes the arguably hard part of this problem. How do we determine V out? Right. Simple application of Kirchhoff's voltage law around this loop tells us that V out is going to be 2 volts minus the voltage drop over the 500 ohm resistor, where the voltage drop over the 500 ohm resistor is just 500 times IC. So let's tuck that in over here. V out is 2 volts minus 500 ohms IC, which becomes 1.423 volts. Okay. So I'm going to ask you guys a question that I hope you know the answer to. Is this circuit operating in the forward active region or not? how can you say that definitively?
The current is flowing the proper way through the diode, and it has a negative voltage drop over it.
So what are the two conditions for the transistor to be operating in the forward active region? VBE needs to be positive. VBC needs, okay, yeah, so VBC would need to be negative, okay, or VCB would need to be positive, okay? So is that true? Yeah, right? So how do we determine what VCB is here? Exactly right. Yeah. So since V out is 1.423 volts, that's significantly larger than 0.8 volts. So this quantity VCB, let me write it up here up top, plus minus VCB, we can observe to be positive. And if the quantity VCB is positive, that means our base collector junction is reverse bias, okay? So let me ask a different question. What is the largest value of RC, our collector resistor? What's the largest value that can have keeping this device in the forward active region? How do you think we should go about figuring that out? The next thing that we're going to talk about is saturation operation. So I want to know effectively what value of RC forces this guy at the edge of saturation. Okay.
Greater than 0.8 volts.
Okay, that's definitely one way to think about it. So if actually though, wouldn't it be if V out is less? So at V out is exactly equal to VBE, or VCE is exactly equal to VBE, then that means that our base collector junction is unbiased. Does that make sense? So that's our transition between that junction going from reverse bias, which is in the forward active region, to forward biased, which would be the saturation mode of operation. Okay. So we need to solve this guy in such a way that VBE and V out are the same. Okay. So that's fairly straightforward. So let's see, do we have enough room here to do it? So if we want V out minus VBE is less than or equal to 0, because V out less than VBE puts us in saturation. Then we know that V out, which is just 2 volts minus our collector current, in this case 1.153 milliamp, times RC is less than or equal to 0.8 volts, which means we have negative 1.153 milliamps times RC is less than or equal to 0.8 volts minus 2 volts, and therefore RC greater than or equal to positive 2 volts minus 0.8 volts divided by 1.153 milliamps gives us our threshold. So that is 1.2 divided by 1.153, or 1040.763. So any RC greater than that value will force our system into saturation operation. All right. Anybody have any questions about this bit right here? Why do I get to just put in the IC value that I calculated previously? VBE is a constant value. Absolutely right. Okay. So just because that VCE changes, our collector emitter voltage or our output voltage obviously changes. IC, as we understand it right now, is only dependent on the quantity VBE, which remained unchanged. All right. So let's talk about saturation mode operation now. Or NPN JTs explicitly. All right, so I'm going to start with my big, huge picture again. And we're going to walk our way through what's happening. So up here on the top, we have our collector. That is lightly doped N-type. In the middle of our semiconductor sandwich, we have our base, which is heavily doped P-type. And then on the bottom, we have our emitter, which is very heavily doped N-type. We're going to have two voltages. VBE. And another voltage up here. VCB. And our emitter terminal is going to be our ground. All right, so for saturation operation, we mentioned this a moment ago. The base emitter junction should be forward biased or reverse biased. Donald, do you know? Jace, what about you? Our base emitter junction. Yes, so we're looking at saturation operation. Forward bias, yes. So if our transistor is on in anything that isn't cut off, well, I take that back. In anything useful that isn't cut off, the base emitter junction needs to be forward biased so that we have the opportunity for charge carriers to diffuse from the region that has a whole bunch of excess charge carriers to elsewhere in the circuit. Okay, so our base emitter junction needs to be forward biased, which means VBE should be greater than 0 volts. In saturation operation, our base collector junction should be reverse biased. So for the polarity that I've drawn here, where we're looking at the quantity VCB, we want 0 volts to be greater than VC so that our base is the highest point of electric potential in our system. Okay. Obviously, the more negative VCB becomes, the more reverse bias this junction becomes, or excuse me, forward bias that junction becomes. Okay. So without drawing all of the bound charge and all that kind of stuff like we did last time, based on the bias conditions here, we should expect to see that the barrier potential of the base emitter voltage is small, or at least smaller than in an unbiased state. And the barrier potential of the base collector junction is also small, or at least smaller than it was in an unbiased state. What does that mean for diffusion of electrons from the emitter to the collector? Or excuse me, emitter, from the emitter to the base? Is it more likely to happen or less likely to happen? More, right? So the barrier potential is smaller, which means we should see electrons can diffuse from the emitter to the base, and transversely we should see that holes can diffuse from the base to the emitter, giving us an emitter current, IE, flowing out of the emitter terminal, right? Positive current is in the opposite direction of electron flow. So this is still going to be dominated by the electron movement. Since the electrons are going up, our positive current is flowing down. Now let's talk about what's going on for our base collector junction, okay? So in the forward active region, these diffusing electrons would get swept through by a large electric field, right? Causing a committer current, a collector current flowing down, okay? They're not going to get swept through by a large electric field because a large electric field does not exist here, right? Since the barrier potential between the base and the collector is lowered, the electric field strength between the base and the collector is lowered, so we only have a small field, okay? So what that really means is that there should be diffusion of electrons from the collector to the base now. Okay. Since the collector is so much more lightly doped, that number of diffusing electrons from the collector to the base is much, much smaller than the number of electrons that are diffusing from the emitter to the base, okay? So what do you think is going to happen? There's going to be a pretty good amount of recombination, sure, but remember that the width of this base is short, such that not a lot of recombination. The width of the base is shorter than the diffusion length of these electrons, right? So they're still going to come across, and effectively there's going to be canceled out by some portion of these diffusing electrons from the collector to the base. Now, we'll talk about that in a second as well, and it might be a little bit easier to understand. We're going to have holes diffuse from the base to the collector because this junction is forward biased, right? The direction of these holes takes away from the collector current. They're flowing in the wrong direction, right? They're flowing opposite the direction of the collector current. And so what we should see is that our collector current, IC, is now equal to IS EXP VBE over VT, which is what our collector current was in the forward active region, minus ISC EXP negative VCB over VT. So our collector current is reduced by the diffusing carriers across the base collector junction, where ISC here is different than IS because they have different areas. Right? That's the first thing that we talked about. Okay. The different areas of the different junctions in this system. So these are two different scaling currents or saturation currents, where this one depends on the area of the emitter junction or the base emitter junction. This one depends on the area of the base collector junction. And obviously this guy depends on the collector base voltage. So this is just diode current for the collector base voltage effectively, right? So what's going on with the base? What do you think should happen to the base current? Should it go up or should it go down? Raise your hand if you think it should increase. 3. So 4, 5, 6. All right, so 6. Raise your hand if you think it should decrease. Or about the same. And then the rest of you guys just don't give a crap. Okay, it is what it is, I guess. I don't know what else to say. All right, so I thought it should be fairly obvious that it should increase because the base current has to supply a lot more holes because diffusion is now also occurring in 2 directions, right? So our base current IB is supplying holes, same diffusion across the base emitter junction. It is supplying holes to sustain diffusion across the base collector junction. And if any recombination occurs in our base region as well, it's sustaining hole concentrations for that. So we should see that our base current, IB, is IS over beta, EXP, EBE over VT, plus ISC, EXP, negative VCB over VT. So it's literally the exact same equation that we had before, except that we now account for diffusion across the base collector junction, where we subtract from the collector current because the holes that are diffusing and the hole and electron diffusion are taking away from what the emitter is doing. And we get plus here because they're adding to what the base was supplying, or what was previously having to be supplied. Okay. So in this case, beta, and we're going to call it beta forced, is just IC over IB in saturation. And how do you think it's going to relate to beta observed in the forward active region? It's going to be lower, right? Because IC is going down and IB is going up. So this fraction is getting smaller and smaller and smaller, right? The numerator is decreasing while the denominator is increasing. This guy is going to be less than or equal to the beta we observe in the forward active region. The reason why it's called beta forced is because we can force it to have a particular value depending on what voltage VCB we apply. That's it. Okay. So if we looked at the relationship IC versus VCB. Let's start with VCB greater than 0, right? So for VCB greater than 0, we're in the forward active region. So what should this graph look like? Go to your equations that we talked about at the very beginning of the class. Look at it and see if IC depends on VCB at all. No. So I'm going to ask you guys again, what should it be? Just be a straight line, just totally flat, because there is no dependence. So we could just call this alpha IE, whatever it is, okay? Now, for a voltage of 0 volts, let's write some stuff down here. VCB greater than 0 volts is our forward active region, right? When VCB is equal to 0 volts, this is the edge of saturation. And now let's talk about what happens as we let the quantity VCB become negative. Okay. So as VCB becomes negative, what should be happening to IC? Literally scroll up here and look at our equation, right? As VCB becomes negative, we have an exponential of negative times a negative. So this term right here starts to grow. So it starts reducing the collector current, right? What are the values of ISC that we've been, or IS that we've been dealing with? On the order of 10 to the negative 12, 10 to the negative 15, all that kind of good stuff, right? It's going to take some time, or a better way to put this is it's going to take a reasonably large negative VCB voltage to take away any appreciable amount of current from our collector current, okay? So we're actually not going to see it start to fall off until, for a silicone diode, we're somewhere in the ballpark of negative 0.4 volts, okay? So if we call this guy right here negative 0.4 volts, what we should see something like this, and then a pretty steep decay. So for 0 volts greater than VCB greater than negative 0.4 volts, we call this soft saturation. In the soft saturation regime, it's still behaving as if it was pretty close to forward active region, okay? Because we're not able to cancel out an appreciable amount of current. When VCB is less than negative 0.4 volts, the deep saturation region, where a large portion of our collector current is being canceled out by that additional diffusion. Okay. So as a reiteration, in the forward active region, that's where we see most of the work being done in amplifier-based applications. And we'll find out, I think in a couple of weeks at this point, based on the way that I've structured the class, That's largely due to the fact that beta is at its highest when we're in the forward active region, and beta is going to be a key parameter. We already know that it's a gain of some sort in our amplification schemes. Okay? And saturation is used not for amplification because our gain is significantly smaller, which we have observed because IC goes down while IB goes up. It also makes it slower so that it responds more slowly to changing in signals. So forward active region, again, used for amplification. Saturation used much more so in digital signal processing with BJTs. So we need to adapt our equivalent circuit model for saturation operation. So in saturation region, the only change that we make is we throw another forward bias diode into the mix. So here is VBE. Here is IS EXP to the VBE over VT. Here's our collector current. Here's IC. Here's IB. And then between our base and collector terminals, we now have another current ISC EXP negative VCB over VT, and it's flowing in that direction. That's our our large signal model for saturation mode operation. Okay. So these large, when we were dealing with diodes, what was the caveat on a large signal model versus a small signal model? Small signal model we got to use whenever we saw a variation of the forward bias voltage of somewhere around 5 millivolts, right? Large signal models are usable whenever. You know, there is no limit on how large the signal can be. All right. Let's say that we have the following circuit. So this is an example of what's called simple biasing of a BJT. So this is how we can bias a BJT for a specific operating point to be used in an amplifier circuit later. And this is about as simple as we can do it. So we're going to have some resistor RC. We're going to have some resistor RB here. We're going to make this guy really honking big, 100 kilo ohms. This is our collector, emitter, and base. Let's say that IS is 2 times 10 to the negative 17 amps. And beta is equal to 100. So what I want to know is what is the maximum value of RC such that VCB is greater than negative 200 millivolts. So let's start with, what does VCB greater than negative 200 millivolts mean? Soft saturation, right? Kind of dead in the middle. So the expectation here is, even though that we are experiencing, like our base collector junction is reverse bias, this guy is still going to behave as if it were in the forward active region. Okay, so we can do a pretty good approximation of what's going to happen by using our forward active region large signal model to analyze this guy. All right, why do you think that base resistance RB is so large? 100 kilo ohms, right? The example that we did a little while ago, our collector resistance was 500, and then we saw that once it got up onto around 1,000 ohms, we started to push it into, push our region of operation into saturation, right? Why do you think RB needs to be so darn big? We just talked about it. As the base current goes up, beta goes down. So the larger our base current is, the faster that we push ourselves into saturation. So we're always going to use a pretty large base resistance here to limit the amount of base current, because we know that the collector current is in turn dependent on that base current as well. Okay. All right, so this guy is a little bit more difficult of a circuit to analyze than the last one. So let's go ahead and draw our model here. We don't know VBE or IB in this case, right? Which of the two models do you want to use? All right, so let's see what happens if we do that. So let's say that we have .5 volts up here. We have our resistor RC, which we do not know. We have our 100 kilo ohm resistor here. That's our base terminal. That's our collector terminal. This is the quantity VBE. This is beta IB. Here is E. And this is our current IB. All right. What do you think we should do next, Logan? You chose the model. So our ultimate goal is to figure out what RC is, right? We know that the potential difference between this point in the circuit up here and this point in the circuit down here is exactly 2.5 volts, independent of whether we take the left-hand path or the right-hand path. So I would argue that we could write KVL equation and a KVL equation and set them equal to each other. And I'd be willing to bet that IB is going to fall out based on the way that we've written this thing, right? So for the left-hand side, we're going to have 2.5 volts minus 100 kilo ohms times our base current IB, because that's the only current flowing through that left-hand branch. Everybody okay with that? Nothing can branch off and flow anywhere else. Plus VBE is equal to 0. And so we've got a little bit of a conundrum here. Well, let's see what happens. Our right-hand side, we are going to have 2.5 volts minus RC times beta IB. Plus VCE, where I'm going to go ahead and define that real quick. Is equal to 0. So we've got a lot of unknowns as it stands right now, right? IB is an unknown, VBE is an unknown, RC is an unknown, VCE is an unknown. So what are some things that we can do to kind of fix some of the stuff that we have here, right? Kind of eliminate some of these unknowns. So is there a relationship between IB and VCE? Pardon? Yeah, so that's a current source. So yeah. Is there a relationship between IB and VBE? I think so. I think I gave you guys one. So all right. So as a quick aside here, we know that IB is equal to IS over beta EXP VBE over VT, right? So if we substituted in this relationship right here, we would have a single equation where the only unknown quantity is VBE. Or we can rearrange this guy to where we can substitute in something for VBE in terms of IB and solve for that. And because IB is showing up in our second equation, that might be reasonable. But could we do something with this VCE here to where it doesn't really matter which way things go?
Can we just artificially say that it's equal to -200 millivolts? If that's the interval we want.
So VCB is -200 millivolts, okay? But that is, you're on to a little something there, right? So we want VCB to be greater than -200 millivolts. So that's really just telling us what our threshold is, right? So VCB of equal to negative 200 millivolts could potentially be useful. So that would be right here. Or another way to write this without so many negative signs would be positive 200 millivolts VBC, right? So I would argue that we could write a KVL equation around this bottom loop here that will relate VCE to our known quantity of 200 millivolts and our unknown quantity of VBE. Right? So we really have lots of options as to which substitutions we want to do. We just need to kind of settle on something to do. All right. So let's start by just directly substituting this guy. Okay. So we have 2.5 volts minus 100 kilo ohms times IS over beta EXP VBE over VT plus VBE is equal to 0. It's one equation, one unknown. We should be able to solve that for VBE. So you guys go ahead and do it and tell me what you get. Recall that IS is 2 times 10 to the negative 17, B is 100, and let's just make it clear, VT is 26 millivolts. You guys get anything yet? I did too, and I don't know why that's the answer because it shouldn't be. That's much more likely what it should be. When I worked this out earlier, I got 833 millivolts. So I'm not sure why I also got negative 2.5 a moment ago. The right-hand side equation is just 0, isn't it?
But, minus VBE, then would have 8 millivolts fall out.
Okay, I see it. All right. Yeah, okay. I see what you're saying. Yeah. So it should be 2.5, which is the total voltage drop is equal to the sum. And the same thing on the right-hand side equation, actually. 2.5 should be equal. And that should fix the sign. Thank you. All right, so 833.4 millivolts. Let's go with that. So now that we know what that VBE voltage is, we can go into our right-hand side equation, right? So for our right-hand side equation, hold on, let's fix that. Yeah. So for our right-hand side equation, we have 2.5 volts is equal to RC, which we are trying to find, times beta, which we know, times IS over beta, EXP, VBE over VT, betas cancel each other out, plus VCE, where if we do Kirchhoff's voltage law, let's start on the bottom left-hand corner. I'm going to do this out so I don't make any dumb algebraic mistakes like I did a moment ago. Negative VBE plus 200 millivolts plus VCE is equal to 0, which means VCE is equal to VBE minus 200 millivolts. And we should be able to solve that guy for RC. And I get that to be 1,120. We ran out of time, so that's why I'm just giving you a numerical answer. I apologize for applying Kirchhoff's voltage law incorrectly up here. Thank you very much for pointing that out. Race, I believe, right? Yeah. But beyond that, asinine mistake, everything else should be legit.